In the last video, we were looking at oxidation reduction reactions that occurred in the organic environment and introduced some basic concepts. At this point in time, we want to take a look at sort of the more of the details of what takes place within an oxidation reduction reaction, and to try to understand sort of the mechanics of how one can go about balancing the equation. One of the things that happens in this setting is that not only do we have to take into account the elements that are here and make sure that the number of atoms are the same on both sides, we have to recognize that in the process that something gains electrons and something loses electrons, but in the overall scheme of things, that the number of electrons lost must be the same as electrons gained. In this reaction, we're going to look at it in a particular setting, and the setting is an acidic environment, which means that there's going to be an excess of H+ ions present in the aqueous solution. All of these substances up here in the reaction, even though not indicated, are aqueous ions, so there's lots of water present. The first step we want to do is to divide this reaction out into two parts. We want to try to keep together the elements that are the same, when possible, on both sides. So in step one, we're going to take the chromium-containing compound and break it into what's called a half equation. So Cr2, O7, 2-, which is known as the dichromate ion, and then we want to keep the Cr 3+, so in some manner this is changing, and we want to analyze what's going on in this process. So to take a look at this, we notice that this chromium ion already is indicated as having a 3+ charge, so that's clear for us. Over here, we have to analyze what's going on to the chromate in the chromium or dichromate ion. The safest way to do that is to actually break this up into two pieces. We are told that generally oxygen has a -2 charge on each one of the oxides. So we're going to call that a -2. We notice that there are 7 of these, so there's a -14 charge contributed by the oxygens. On the other side, we have 2 chromiums. The sum of the charges on the chromiums and the charges on the oxygens must equal 2-. So one of the rules about oxidation numbers is the sum of the oxidation numbers on each element must equal the charge on the oxidation of the polyatomic ion together. So the question is, what number added to -14 is equal to -2? And that is +12. So that means that there must be a +12 here in total. There are 2 chromiums, so each one of these must be +6. So we've managed here to identify those pieces where we can take a look at the identification of parts. So now we notice that the chromium has gone from a +6 to a +3. We also notice that there are 2 chromiums here, which means that to balance the issue of elements, we have to have 2 atoms of Cr3+ over there. So we've taken care of that part. But we do have to recognize, again, also the change in electrons. So each chromium has gone from a +6 to a +3. So that chromium in the process has become less positive. To become less positive, then the only way you can do that is to gain electrons. So this must have gained electrons. So each chromium finds itself gaining 3 electrons. There are 2 chromiums in total, so there's a gain of 6 electrons. So how can we write this? Let's get it a little cleaner. So here's our Cr2O7 -2. I have to add 6 electrons. When that takes place, I have 2 Cr plus 3 ions. We also notice that on this side there's oxygen, and there's no oxygen on this side. One of the rules when we deal with acids or acidic environments is that if I need to add oxygen, I do it in the form of water. So I have to add water over here. And I have to add as many waters as I have oxygen. So I have to add over here 7 waters. Now, because it is an acidic environment, H plus is very prevalent. So if I need to balance out H's, then I need to do it in the form of H plus. Since it's 7 times 2 is 14 H's. On this side I need to take and add 14 H plus. So this reaction describes the half equation for what takes place to the chromium along the way. Chromium ions have acquired 6 electrons and gone to chromium plus 3. So we're going to box this and come back to it. Ultimately the goal is that I can take these 2 half equations, I can add them together, and I can produce the overall process. So the other piece is to take a look at the nitrogen containing part, NO2 minus, NO3 minus. So NO2 minus 1 goes to NO3 minus 1. Again, we can divide this out. Each oxygen is minus 2, giving us a total of a minus 4. What do I need to combine to minus 4 to get minus 1? I need plus 3. So here the nitrogen is a plus 3. On this side, I have each oxygen being minus 2. This is minus 6. So this must be plus 5. So each nitrogen is plus 5. So I have NO2 minus 1, NO3 minus 1. And in order to get from a plus 3 to a plus 5 state, then that means that 2 electrons have been lost. So on this side, from here, these 2 electrons have been lost. So where did they go? They went to this side of the reaction. So I have this ion plus I have 2 electrons present. Notice again also other things, oxygen here and oxygen here. There's one more O, so I need an H2O. That balances the oxygens. Now I have to deal with H's, so on this side I have 2H plus. And here's my reaction. Okay, so as I look at the pieces, let's get them on the edge. Now the goal is that I want to be able to add these 2 reactions together because the sum of the 2 half equations should give the whole piece. The only problem we have is that here, this has 6 electrons, and this one has 2. So the number of electrons lost have to equal the number of electrons gained. The only way to do that is to look at this equation and say I have to multiply through this to get up to 6 electrons. What do I multiply by? I have to multiply by 3. So to do that, let's take it and identify a different color. So now my coefficients will change. So 3 times 1 is 3. 3 times 1 is 3. 3 times 2 is 6. 3 times 1 is 3. And 3 times 2 is 6. Now I can try to add those equations together and take a look at the overall effect. So what am I going to have as my sum in this process? So I'm going to have a CR 207 minus 2. Let's keep everything together for a moment. I'm going to have my 6 electrons. I'm going to have my 14 H pluses, my 3 NO2 minuses, and my 3 H2Os. On the other side, I'm going to have my 2 Cr3 pluses, or plus 3s, my 7 H2Os, my 6 H pluses, my 3 NO3 minus 1s, and my 6 electrons. Now I can go back and look and see how can I simplify this, which means canceling out whatever is the same on both sides. First things first, 6 electrons are gone because there's 6 electrons over here. Okay, so those are gone. I can look for my H pluses. On this side I have 14, on this side I have 6. So the balance is that on this side I have 8 H pluses. On this side I have 3 waters, on this side I have 7 waters. So the balance is that I have 4 waters. Okay, let's take a look at what anything else I can cancel. Everything else is different. So my reaction now here looks like this. Cr2 07 minus 2 plus H plus 3 NO2 minus goes to 2 Cr plus 3 plus 4H2O plus 3 NO3 minus 1. So by doing this, everything should cancel out in terms of having the same number of elements as well as electrons. 2 chromiums are here, 2 chromiums are here. We have 7, and then we have 6, 13 oxygens. Over here we have 4 and 9, 13 oxygens, 8 H pluses, 8 H pluses, 3 Ns, and 3 Ns. And the charges, electrons, are in balance. So this is the technique that we use to try to make sure that we can compensate for and balance all of the pieces when we do a redox reaction in an acidic environment.